Okay, so welcome back. Let's do this one. It's not a numerical problem to be solved, but it's a problem that can be solved using Bernoulli equation and mass balance. Okay, so what they are asking us to get is the flow rate. Okay, so let's just see if we have this awful, but let's just go with it. So we have this pipe. Okay, so we have a contraction from 1 to 2 as the sentence says. And we have pressure here, we have this diameter, and we have this velocity. And in this part, we have pressure 2, velocity 2, and diameter 2. So the pipe goes on, okay? It doesn't go into the atmosphere, and the pipe comes from the left, okay? So everything is inside a pipe. Now, what you can write from the start is, okay, so you have Bernoulli equation, and you will put this, okay? So it shouldn't be a problem. We have the pressure part, the kinetic part, and the potential or the height part for each point 1 and 2. Okay, so we are writing this. We can assume that C1 equals to C2, so this guy just goes, and therefore we are just living with pressure and velocity in these cases, okay? So we have pressure 1 rho g plus V1 squared divided by 2g equals to, so I'm not putting anything new here, I'm just trying to go with it. Now that I have that, I can write my mass balance. So I'm going to put this mass balance here, and I can say that the flow that it's going in 1 is the same flow that it's going at 2. So I can write that the density times the velocity times the area, the cross-section area of the pipe, equals to rho 2 V2 and A2, okay? So I'm going to assume that this is a liquid. This is a liquid, therefore the density is a constant. So I'm going to put these densities away, and I can see that there is well, there are different diameters. So I'm gonna put it like this. This is the area for 1, and I'm gonna put V2 times the area of 2. Okay, so that's what I can know. Now, from this mass balance, you can see that the pi and the 4 just goes out. Therefore, you can have this expression V1 equals to V2, and then a ratio of diameters. Okay, so that's what you have in them. And these guys needs to be squared. Okay, so that's the way that you can put velocity 1 in terms of velocity 2, or you can also put V2 equals to V1 and back the other way around with the diameters. Whichever you want, you can do it, okay? So I think I'm gonna pick this one, that is V2, because most of the time you have information at the upstream, and then you don't have many times information at the downstream. Nonetheless, now you can substitute this guy over here and keep on working. So let's just keep on working. I'm gonna put it this, I'm gonna try and put this, the pressure to my left. So it's gonna be rho g, and this is gonna be equal to, okay, not yet. And therefore, instead of putting that, I'm gonna put this plus and then V1 squared 2g equals to V2. But instead of V2, I'm gonna put V1 squared, okay? And then D1 divided by D2, and then to the fourth, because it's actually squared, the square of the diameters. And everything's gonna be divided by 2g. Okay, now I'm going to pass this guy over here, and you can see that I can factorize that expression. This one's going to be equals to V1 divided V1 squared divided by 2g, and then I'm going to have this D1 divided by D2 to the fourth minus 1, because this guy over here is multiplied. This one is multiplied by 1, okay, and it's going to pass with a minus sign, so that's why I have that thing there. So I'm gonna make my life a little bit easier, okay? And I'm gonna put, we still haven't found the flow rate. We have used so far Bernoulli equation and mass balance, okay? So what I want to put somewhere there is the flow rate. So you can say that the flow rate equals to the flow rate that is going through 1, and it's also the same thing as the flow rate that is going through 2. So you can write these ones, and you can pick whichever point you want to use, whether you want to use 1 or whether you want to use 2, you can do it. So I'm going to put it like this, and then P2, the square divided by 4. So maybe you can think that I have put V1 there, okay? So I have put V1 there, so I'm going to pick this one over here. Okay, so if I do that, I'm gonna have P1 minus P2 rho G equals to V1 squared, but instead of V1 squared, I'm gonna put this stuff squared. Okay, so it's gonna be a little bit messy, but let me just go with that. And then B1 squared, okay? And then, no, that's not the thing. Oh, sorry, guys. So Q and then 4 multiplied by 4 and then pi divided by pi and then d1 squared, and this is equals to v1. Okay, so this is equals to p1. Then I'm going to square this. Okay, so instead of putting v1 squared, I'm going to put the q. Okay, so I'm going to square this whole expression and put it in there. Okay, but before that, yeah, I'm going to do something else. So hopefully you can keep up with what I'm gonna put here. So these two pass through here, okay? The G just goes out. This one just eliminate. And then I'm gonna pass this stuff, this old fella, I'm gonna pass it dividing by that. And then I'm gonna square root everything. So this is how we look, okay? This is how we look. I'm gonna put these two over here, okay? The G is just out. The density, it's still there, okay? And I need to put this factor. So this guy is gonna be down there, okay? It's gonna be dividing because here is multiplying, and then it's gonna be square root of that. So what I'm gonna put there, what I put there is this. It's gonna be square root of this times beta. So beta, it's just something that I just made up, and this one's gonna be equal to V1. So take a look. Beta should be equal to, hopefully I'm gonna do this right. It was this D1 divided by D2 to the fourth minus 1. So I passed it down. I just pass it down. So it's gonna be a minus. It's gonna be in the denominator, and I square root that. Therefore, it should be like this. So this is the definition of beta. I know it's a little bit complicated with the algebra. It shouldn't be that complicated. You can do this exercise as many times as you want, and you will get to something like that. So hopefully you can understand that just regarding geometry, D1 and D2, this factor is just because of geometry. So if you build a pipe and you know the diameter ratios, okay, so you can actually find this beta. So it doesn't depend on anything else but geometry. So that's why it's useful just to put it like this. Remember, P1 is not dependent on geometry, P2 is not dependent, rho is not dependent. So the only thing that depends on geometry in this case is this beta here. And that's my expression for V1. I still do not want to get V1. I want to get the Q. Therefore, I'm going to write here, so this is 4 times Q divided by pi and then d1 squared. Okay, so I'm going to pass everything to the other side and I have arrived to my expression. I'm going to put it like this again, so in black. So I'm going to put, so 2 and then difference of pressure between 1 and 2, the density, I'm going to square root that. Everything is being in this square root times beta times the pi divided by 4 and then d1 squared, and this one should be equal to the flow rate. Okay, hopefully you can see that this, guys, is also just depending on geometry. You can actually do more algebra and try to put d1 squared inside this expression, but it's something that is not that very relevant right now. So that's my expression for the flow rate using Bernoulli equation, mass balance, and that's it. Okay, so I will see you